All right, everybody, welcome to the video here for lesson number 1 on the normal distribution. So in this unit, since we are like hardcore into distance learning right now, I'm not going to have you do homework assignments with all of these lessons. The goal here is to learn. If you can learn, we're in good shape. Okay, you'll have a couple problem sets here or there, but for the most part, you're just going to be watching videos. Can you learn what I'm talking about, and can you apply it later on? So the first thing that we see here is in the title of the lesson. So it says normal distribution. What is that? Well, what distributions are is that's a way for us to take what we just did in probability and extend it into statistics. Probability and statistics have this length, and distribution has that mathematics that allows us to make that link between the two. So what we have to be able to do before we can do anything with the normal distribution is we have to understand a couple things about what a distribution is. So we're going to take a bunch of data, we're going to put it into a dot plot, we're going to put it into a histogram, or we're going to put it into what we're going to see here, these like bell curves, and we're going to be able to look at that data and see things about it and be able to say, all right, I know where this piece of data fits according to all of the other pieces of data. So when we talk about shape, there are three basic shapes of a distribution. So one shape of a distribution is going to have a really big bell at the beginning, and then it's going to taper out towards the end. So we'll have a lot of values at the bottom and not so many values at the top. Okay, this is what we call skewed right. The values on the right of this distribution are going to skew the data. So an example of something that would be a skewed right data would be if you took all of the different people that are currently right now in my class, right? So you take all of the different people in my class, most of you are in your, 15, 16-year-old range. You're all right here, okay? I am 36 years old, so I'm going to be way over here. My age, if it was included in your data, would be skewing the whole average and everything for that shape. Another example of a distribution would be something that has a lot of values at the top, but not so many values at the bottom. This would be like if I gave you a really easy test and everybody got 90s and 100s, but a couple people really didn't do so well and they got something like in the 40s. This is an example of a skewed left graph. Now, for all purposes for this course, skewed left and skewed right graphs, you're not really going to see again after today's lesson. But I could ask you a question like, which of the following distributions is skewed right or skewed left? And you should know what that vocabulary word means. The one we're mainly going to focus on are these graphs that are like perfectly shaped. And these perfectly shaped graphs are going to be approximately normal. Now, what that means is these graphs are symmetrical. So if we have a symmetrical distribution, that means all of our data fits into it perfectly, where half of your data is above the middle and the other half is below the middle. This is what we want, and this is what we're going to focus on a lot for the first couple lessons and actually throughout all of statistics. So if you're somebody that signed up to take AP statistics next year, you're going to do this literally for the entire school year next year. Now, when we're talking about a distribution, we can talk about the center of the data set. Now, when you were back in Algebra 1, you did centers of data sets. You talked about the median of a data set. So whoever your Algebra 1 teacher was might have given you, 10 different random numbers and said, what's the median of this data set? You put them in order and you found the middle number. That's one way of determining the center. There is, however, another way, and you did this as well in Algebra 1. It's called the mean. So the center of an approximately normal graph is going to be the mean of the data set, or the average of the data set. The other vocabulary word that we're going to talk a lot about is the spread of the data. So when we're talking about data, we're talking about how that data fits into each other. And one of the things that we can do is see how the spread of the data allows us to say our data is really close to the mean or really far away from the mean. We call this the variability of the data. So there are different types of data that we have. So if our spread is a really large number, that means there's lots of variability in my data, meaning the data pieces are really far away from the mean. If our variability is really small, then we can say, all right, our data is really close to the average, and we can talk about that as well. There is a vocabulary word that goes along with the spread of the data, which we're going to talk a lot about, which is called standard deviation. Now we're talking about standard curves here. We're talking about approximately symmetrical curves. So when we're talking about a standard deviation, we're talking about units of measurement that show us how far a piece of data is from the mean of the data set. Okay, so if the average of something, say it's an SAT score, right? The average SAT score is 1,000 and you got a 1,400. How far are you from the mean? That's what standard deviation allows us to find. Okay, another example would be if you're talking about the average height of human beings, right? If you take somebody like Shaquille O'Neal, who's like 7'3" tall, he would be a very large standard deviation away from the mean. Where if you take somebody like me, for example, who's 5'9", 5'10", somewhere around there, I'd be right toward the middle of the data set. I'd be right in that average range. So let's talk a little bit more about this normal distribution that we're going to spend so much time with. So the normal distribution does this for us. So you're going to see this is a nice, what we call this a bell curve. And if you look at 0, 0 represents the mean of the data. So whatever that data is that you discovered or that you found, the average is going to be here. And I'm going to make a dotted line right down the middle of this bell curve. And what we see here is half of our data is above and the other half is below. In a normal distribution, this will always be perfectly half of our data above and perfectly half of our data below. Now, what we can now do with this normal curve, you're going to see these other numbers down here. These other numbers down here represent the standard deviations above the mean and the standard deviations below. Not below, below the mean. So if you're going to take the average height of a human being, right, my 5'9" self is going to be somewhere here towards 0 because I'm going to be really close to the average height of an adult male. Shaquille O'Neal is going to be way over here someplace because he's going to be like way above the normal average, so showing your spread. Right, some of the taller individuals here, you might be somewhere here if you're like 6'1", 6'2", and some of those shorter individuals will be down here. So what else do we now know about this bell curve? And I'm going to erase some stuff here. I know you're probably taking notes along with me, but you could always refer back to the video. Okay, so in this particular bell curve, what we have are a bunch of different standard deviations. And if I separate this out into a couple sections, one standard deviation above, one standard deviation below. Notice this is a big section of this bell curve. This section represents 68% of the bell curve. So what we can say is 68% of the data falls within one standard deviation of the mean. So one above or one below. So if I was to talk about some data set and you knew that that piece of data, one single piece of data, was within one standard deviation of the mean, there was a 68% chance of that happening. Now, if I make this a little bit wider, so instead of doing one standard deviation above the mean, if we talk about two standard deviations above or below the mean, how much of this are we talking about now? So if I go between these two red pieces are going to represent 95% of my data. So we can say 95% of data falls within 2 standard deviations of the mean. Meaning most of my data is going to fit between 2 standard deviations of the mean. And we're going to spend a lot of time with that particular concept. There's like 4 lessons at the end of this chapter where we're going to look at data and say, is it probable that that data set fits into this, or that piece of data fits into this data set? If it doesn't fall within this range here, it's not probable, right? Think about it, right? If I said, pick a random person that walks into the Cornwall High School and figure out what their height is, 95% of people are going to fall here. Right? There's only going to be those very few people that are shorter than that and very few people that are taller than that. And the last data piece that we'll look at here from this normal distribution is between 3 standard deviations above or below the mean. Now this number is going to be 99.9% of data. Almost every single piece of data will fit between 3 standard deviations above or below the mean. Okay, very few pieces will be outliers above or below that number. So let's take a look at the math that we could actually do with this. Now that we know a little bit of background about what a distribution is and what the normal distribution does for us, we can do some things with some math. So it says use technology to determine the proportion. So it says the proportion of a population that is more than 2.63 standard deviations above the mean. So to do this, we have to use our calculator. So let me pause my video here and pull up my calculator so we can use it. Okay, so I have my calculator ready to go. Before we jump to the calculator, though, we have some things we need to look at here. So let's make a nice little bell curve. So 2.3 standard deviations above the mean. So the mean is here. This is at 0. 2.63 is going to be somewhere over here. And I want to figure out what portion of my data is going to be above that. Now, this goes on forever to infinity, right? Now, when we think of data, I just said before, 99.9% of data falls within 3 standard deviations of the mean. So think about what percent of the data falls within 5 standard deviations of the mean or 10 standard deviations of the mean. You're talking about percents that are so small, they don't matter anymore. So what we have to look at is what's the lower number and what's the higher number. So we're going to say the lower, we call this Z-score, which we'll talk a little bit more about on the next page. Just write it down for now. That's 2.63. That's the lower number. The higher Z-score, we're just going to say 10. Whenever we go up forever or down forever, we just use -10 or +10 because that's usually plenty enough to get to our number. Now, what is Z-score? Z-score is the value that represents where you are on the bottom here of this normal distribution. It represents how many standard deviations you are above or below the mean. It's just a fancy name for that number. So how do we figure out what this proportion is? What is the percent of data that fits into this little colored in area of my normal curve? So to do that, we're going to go to our graphing calculators. There is a button for distribution. If I hit second and then the vars button, notice it's still highlighted in red on my calculator, right? This gives us the distribution menu. There's a ton of stuff in here, but there's only one thing you're ever going to use, and that's option 2, normal CDF. If you take AP Stats next year, you might do this other stuff, but for this class, only ever use normal CDF. You're going to hit enter. The lower number was 2.63. The upper number was 10. These two things represent things. This represents the mean. That fancy U symbol represents the mean of our normal distribution. And this weird looking symbol with a tail on top represents the standard deviation number. These two numbers are always going to be 0 and 1. Never change them. Go down to where it says paste, hit enter, and then hit enter again. Now, if you have an old calculator, you don't have the new fancy one like I have, it's going to look like this. Just type in your lower number, comma, your bigger number, comma, 0, comma, 1. The comma button is right here, right above 7, if you follow my cursor here. Hit enter, and here's our proportion. So we can say 0.0043. So we'll say 0.0043. So our proportion of data that falls above 2.3 standard deviations above the mean is that. We can even transfer this to a percent and say 0.43% of data will be above 2.63 standard deviations. That's what we're finding. A very, very small portion of our data is going to fall above that number. Because we just said between 2 standard deviations is, 95% of your data. So if we're talking about the numbers that are above 2.63 standard deviations, it's going to be a very small percentage. Now let's try another one. So it says the proportion of a population that is less than 1.5 standard deviations below the means. So if we take our bell curve, we put 1.25. 1.25 is going to be, on the right side of 0. And I want to say below. So I want to color in or shade in this whole area below, going all the way down to -10. So what's my lower number? My lower z-score number is -10. My upper number is 1.25. Right? Always read your z-scores from left to right. So when we normal CDF this, we're going to make the lower number -10. So if I go back to my graphing calculator, second vars for the distribution menu, option 2. The lower number, we're going to make -10. The upper number, we're going to make 1.25. Go down to paste and hit enter, and then hit enter again. So we should have a really big portion of our data should fit that description because we're talking about below 1.25. If I look at my curve I made, I colored in a big section of this, right? And when I look at this proportion, it was 0.894 or 89.4% of the data. So almost 90% of your data is going to fall within this range of numbers here. Notice this is really just calculator work, right? Understand what the words mean like we did on the first page, and now it's just calculator work. Next question says, what is the portion of the population that falls between 1.4 standard deviations below the mean? Oh no, I think I made a mistake. What is the proportion of population that is less than 1 point standard deviations below the mean? I made a boo-boo here. Erase this. This is all wrong. Tends to happen. All right, let's fix this up. That was wrong. See, reading is tough. So since it says below the mean, we actually should have done -1.25 and show below the mean, down to -10. It's going to make a difference. That's going to be less of a proportion. It's still going to be a relatively big number, not 89%. So the low number, we'll do -10. The upper number, we're going to do -1.25. So seeing that one word there, that messed me up. I apologize for that. So let's go back to our calculator and fix this up, right? So if we go second, distribution, option 2, make that upper number -1.25. Go down to paste, we'll fix this up, and there we go. That seems a little bit better. 0.1056, so we'll say 0.106, we'll just round it. So we'll say this is 0.106. So about 10.6% of your data is below that number. So again, reading here is important, obviously by my mistake. So let's take a look at the next one. So it says a proportion of a population that falls within 1.4 standard deviations below the mean. So let's make our bell curve. Let's label it correctly. Negative 1.4, that's below the mean, so that's below 0. And 1.87 standard deviations above the mean, so we'll say 1.87 above the mean. So our lower number is negative 1.4. Our upper number is 1.87. So if we go ahead and type those into our calculator, so we'll go normal CDF again. Those numbers are negative 1.4, negative 1.4, and positive 1.87. Check that. We're good. Go down and paste it. Hit enter again, and we have a big proportion of our data. So if we look at this, we have 0.889. So we'll say 0.889. So we're talking about this portion of our data. Now, if you look, that's a big portion of your data, right? We know that between 1 standard deviation above the mean is about 68%, within 2, right, is 95%. This is going to fall somewhere in between those because we're not quite at 2 here. Okay, so again, just knowing how to use the calculator, right? Again, 88.9% of your data is going to fall within that section of your bell curve. Okay, let's talk a little bit more about that word I used before, z-scores. So what is a z-score? The z-score is the number of standard deviations a value is above or below the mean. So what we were typing into the calculator on the previous page were z-scores. But those z-scores were just given to you, right? I'm telling you that it is 1.87 above the mean, right? Sometimes you don't know what the value is. So sometimes we have to calculate the z-score. So to calculate the z-score, we have to figure out how far is the value away from the mean, and then divide it by the number of standard deviations that we have. So when we're talking about a set of data, the standard deviation is telling us the variability. It's telling us how much the data is spread out. So we need to know the mean, we need to know the value, and we need to know the standard deviation of the data to find its z-score. All of those things are going to be given to you. Okay, so you just have to know how to calculate the z-score. So number 2 says the price of printers in a store have a mean of $240 and a standard deviation of $50. The printer you eventually chose is $340. This is the mean. This is the standard deviation. This is your value. So those are the 3 pieces that fit into this z-score formula. So it says, what is the z-score for the price of your printer? So I can say the z-score is equal to my printer value, $340, minus the mean, $240, divided by the standard deviation of 50. So my z-score is going to be 2. So this means your printer cost is 2 standard deviations above the mean printer cost. So when you make your bell curve, your printer is going to be here. Here's your printer. So you can do one of 2 things. You can do normal CDF to interpret the meaning of this and figure out what percent is below 2, or you can find what percent is above 2. I'm going to do below 2. So my lower number is negative 10. My upper number is 2. This is going to calculate the portion of printers that cost less than the printer that I chose. That's going to interpret this meaning of my z-score so I know how my printer fits into the rest of the printers that were available for me to buy. So if I do normal CDF here, I'm not going to keep clicking back and forth there. I think we have that by now. So if I do negative 10 for my lower number and 2 for my upper number, we wind up getting 0.977. So what we can say is 97.7% of printers cost less than $340, according to the data that they provided for me. Number 3 talks about this guy named Ashish. It says Ashish's height is 63 inches. The mean height for boys at his school is 68.1 inches, so he's below the average. And the standard deviation of boys' heights is 2.8 inches. Again, standard deviation is just talking about how far apart the data is spread. So are the boys consistently really close to the mean, or are they spread out really far from the mean? So that data piece is given. What's the z-score for Ashish's height? So we can say the z-score is, well, what's his height? 63, minus the average height at his school, 68.1, divided by the standard deviation of heights of boys at his school. Do some quick math here. And you get a z-score of negative 1.821. 3 decimal places is usually good enough. So when we look at the bell curve and we talk about Ashish's height, here's 0, negative 1.821 is down here someplace. So we can do 2 things. We can calculate the percent of people that are taller than him, or we can calculate the percent of people that are shorter than him. Let's go with taller this time. So what we can say here is the lower number is the negative 1.821 number we found. The upper number is just 10. So if we do normal distribution, CDF, we do negative 1.821 and make the upper number 10, we wind up getting 0.966. So what we can say here is 96.6% of boys are taller than Ashish. Number 4 says, working with normal distributions, we can calculate the following probabilities. So this probability, right, that's what we're finding here, right? We're calculating the probability that you're falling above or below a certain number. So here we want the z-score to be less than negative 2.15. So the lower number, right, if we were to make this bell curve, what are we trying to calculate here? We have negative 2.15, and we want to calculate lower. Less than means lower. So the lower z-score we'll use is negative 10. The upper z-score that we'll use is negative 2.15. For this middle one, we would say, all right, 1.67, and, well, that's in the wrong spot. Let's try that again. All right, so we want to be between 1.67 and 2.55. So I have 1.67, that's going to be above 0. And we have 2.55. So we want to calculate the probability of falling here. What's the percent, or what's the proportion that is there? And this one says greater than negative 1.2. So if I make my bell curve, right, I have negative 1.2, and I want to be greater than that, so I want to go all the way up to 10. So here my lower z-score was 1.67. My upper z-score is 2.55. Here my lower z-score is negative 1.2, and my upper z-score is 10. I'm going to pause the video. I'm going to type these into my calculator. I want you to try and type them in your calculator yourself. If you have to rewind the video and go back to where I was on the calculator so you could see how you're doing, right, or see how to do it if you're confused. But I want to have you kind of try some here on your own here for a minute. All right, so let's see how you did. So for the first one, I got a proportion of 0.0158, which converts to 1.58% chance of happening. The second one, I got 0.0421, which converts to a 4.21% chance of happening. And for the last one, I got 0.885 as my proportion of data, which converts to an 88.5% chance of happening. So again, this number we're getting in my calculator is the proportion of data. We can convert it to a percent to determine the percent chance that our data falls within that section of the bell curve. That's lesson 1. Hopefully that helped. Email me if you have questions, and hopefully I get to see you all soon.